this is the title, and this talk will consist of two parts. One will be more representation theoretic about the orbit method, and the other will be more geometric about the deformations of singular symplectic varieties. So I start with G, and this is going to be a V algebra. All complex numbers. And you should think about, well, maybe you take a vector space V and take its endomorphisms. Or my running example for this talk will be the V algebra SO2, which is just the algebra of 2 by 2 matrices with trace 0. And in both cases, the V bracket is a matrix commutative. So now I'm a representation theorist. I want to study representations of G meaning homomorphisms into the algebra of this kind. And I'm most interested in irreducible representations, those without sub-representations. So a big question is to classify all irreducible representations of G. When I say all, I mean both finite and infinite dimension. So usually I assume that the dimension of G is finite, but it still makes a lot of sense to look at infinite dimensional representations. And there are two things which you need to know about this question. First is the bad news. This question is what? The reason is that there are way too many infinite dimensional irreducibles to classify them. So this is bad. However, good news is that this problem has replacement. Instead of irreducible representations, I will look at the annihilators in the universal enveloping algebra. So let me explain what this word means. So I consider universal enveloping algebra. This is an associative algebra, U of G, which is formally defined as follows. I take the tensor algebra of G, and I go down by all relations of the form x tensor y minus y tensor x minus x bracket y. And what this really means is that a representation of this associative algebra is the same thing as a representation of the V algebra G. Okay? Now I'm ready to give the main definition of this first part. So a two-sided ideal I in U of G is primitive if I is the annihilator in U of G of some reducible representation M, where annihilator means all elements acting by zero. You can say the kernel if you want. So this is all elements X in U of G such that X acts on M by zero. Okay? And then I get the set which is more tractable. There are much fewer possible annihilators. Well, it's easy to see that if you have two finite dimensional irreducibles with the same annihilator, they must be isomorphic.
What's M?
M is a reducible representation, some irreducible. So maybe I should say if there is M, such that this holds. Okay? So if you can have two more isomorphic infinite dimensional reducible representations with the same unit. So this is a way more reasonable problem. And let me give you an example for G equal to SL2. Well, here I have basis elements, which are usually denoted by E. This is the matrix 0, 1, 0, 0. I have H, which is 1, 0, 0, minus 1. And I have F, which is 0, 0, 1, 0. Now, what is the universal enveloping algebra? It's a quotient of the free algebra in these generators. By the commutation relations between these three guys, and these relations are very classical. They are H bracket E is equal to E, H bracket F is minus 2F, and E bracket F is H. And I want to describe their primitive ideals inside of this algebra. So the primitive ideals are well, there are finite dimensional reducible representations which are just classified by their dimension. So for any n bigger than 0, I can consider the annihilator in U of G of n-dimensional irreducible representation. That's a primitive idea. Now, there are also primitive ideas of infinite codimension, and they're parameterized by complex numbers. So if I take a complex number z, I can produce the following gadget. I can take U of G times the following element for Fe plus H plus 1 squared plus Z. That's a legitimate element in my algebra. It's central, it commutes with everything. So this is a two-sided ideal rather than left ideal. And so this is two-sided ideals. Ideal. And it's primitive. A module annihilated by this ideal is an irreducible Verma. Okay? And in fact, these are all primitive ideals without repetition. So pretty easy to describe. Okay? So maybe I should introduce some notation. So I will write prim G for the set of primitive ideals in U of G. Now this has been studied for a while, and there is a case where you can get a reasonable complete description. Somewhat surprisingly, that's the case when the Lie algebra G is nilpotent. It's not so important to know the definition. Let me just give you an example. I can consider the Lie algebra of, say, strictly upper triangular matrices, like such. And this is an important Lie algebra, okay? Now what can I do with Lie algebra? I can consider the corresponding group G. For example, in my example, I will get the group of all unitriangular matrices. Ones on the diagonal, 0 below, and whatever you want above. And then, in general case, this V group acts on the Lie algebra via adjoint representation. So I can take adjoint representation. For example, here it's going to be given by matrix conjugation. So G applied to X is equal to Gx G minus 1. And then what I want to do with this, I want to take the dual representation. I want to take the action on G of G on the functions on small g. Okay? Now there is a theorem due to Dixmier back to, well, 63. And let me call this theorem algebraic orbit method. I will later explain why I say algebraic. What the theorem tells you is that the set of primitive ideals in your G is a natural bijection. It's very important that the bijection is natural with G star mod G. And this is just a set of orbits. So you can take an orbit in G star and naturally produce a primitive ideal. And you get primitive ideals in this way. Okay? Also. Now I think some remark is necessary. So this set here is not a piece of cake, it's a piece of something else. But still you can hope to use some geometric methods to describe it. While the set of primitive ideals a priori is something completely weird and you cannot understand. Yet they are isomorphic. Okay? So let me explain what algebraic refers to. So Alexander Kirillov Sr. I guess at that point he wasn't known as a senior. So in 61 proved that in fact unitary irreducible representations of the group G are in rational bijection with G star G. So this is known as the orbit method. Okay? But then surprisingly primitive ideals are classified in the same way. Now, of course, while we like nilpotent algebras, we prefer semi-simple ones. And the question which arose basically around that time is how can we generalize this to semi-simple algebras?
Sorry, can I ask?
Sure.
So in this theorem of 63, and compare with the example of SL2, can you give us an idea of what G star is and compare it with the example?
So in this example,
Yeah.
G star is
No,
something.
no. The SL2 example?
In the SL2 example, G star is the same as G. I was about to say this. The SL2. So the third part is, well, orbit method for semi-simple algebras. So what algebras do I consider? I can have G equal to SLN. These are square matrices of trace 0. Or maybe I can have SLN. These are skew symmetric matrices. Or maybe I can consider SP2N. These are symplectic matrices. Or 5 exceptional algebras. This is what I care about. Now in this case we are fortunate because G and G dual are the same. We are what is known as killing form. And then basically this becomes the set of adjoint orbits. Orbits here under matrix conjugation. And this is easy to classify. So G mod G is known and easy. Well, if you have SLN, then basically the answer is given by the Jordan normal form theorem. And then in general, I mean, a very similar result holds. So this is easy to consider. Now, bad news is that primitive ideals. The set of primitive ideals is known and hard. For experts, what you do, you take the Cartan subalgebra of G, and then you model out by a pretty fancy equivalence relation. So this is hard. This was done in the 80s, and classification was completed by Barbash and Vaughan, which used results of people like Cartan and Lustig and of Joseph. One thing to know about this classification is that there is no direct relation to this set. This is not directly related to the set of adjoint orbits. Moreover, this set here is somewhat larger in a suitable sense. So, we no longer expect to have a bijection between the two. Okay? So this one is larger. Guys, I'm going to see it if I write here. Okay, so then comes the main result of the first part, which is due to myself from 2016. And this says there is a natural map from G1G to primitive. So I can take an adjoint orbit and I can naturally produce a primitive ideal. Moreover, this map is almost always known to be injective. Almost always. Injective, and conjecturally injective in general. So the cases where we know that it's injective includes let's say G equal to SLN, SON, or SP2N. And also we know this for most ideals and exceptional ideals. So it's like it's as much as you can hope to get. You can hope to get a natural inclusion, and this is indeed the case. Modular a few curiosities of exceptional biology. And then you can actually at least give a conjecture on what the image is. Let me not talk about it. Okay? So, I want to finish this part by giving an example of G equal to SL2. So let's see what happens for SL2. So, what kind of adjoint orbits do we get? Well, we have orbit 0. And this goes under this map to the annihilator of C, of the trivial of C. And then we have a family of orbits parameterized by complex numbers. So we can have orbit which I will call O sub z. And this is the orbit of a matrix of the form square root of z, 1 minus square root of z, 0. Okay? When z is non-zero, this matrix is generalizable, and when z is equal to 0, we get a Jordan normal form, right? And you can say that these are all non-zero matrices with determinant equal to z. Such guys form a single adjoint orbit. So where does this go? Well, it goes to the ideal generated by that funny central element for Fe plus H plus 1 squared plus. So that's an example. And in fact, you can see this mapping conceptually, which will be explained later. Alright. So
So what you don't get are annihilators of finite dimensional representations other than trivial.
Yep. This I know that. For some conceptual reason. Alright. So, a few things to say. First of all, why should we care about having such a theorem? Well, for nilpotent Lie algebras, I also have unitary irreducibles in the picture. And so this has been classified, at least for classical types, but the problem is that classification is very non-conceptual. So one reason to believe this theorem can be useful is to try to understand the existing classifications in a more conceptual way. Now, just to preview, the way how this is proved, I will be looking at certain singular symplectic varieties, and I will be comparing their non-commutative deformations and their commutative deformations. And from doing this, I can prove this theorem. So this finishes the first part of the talk. And now I'm going to switch to a more geometric story, and in the end, I'm going to link the two stories together. Okay? So, let's talk about singular symplectic varieties first. Well, before going to singular, let me remind you what smooth symplectic variety is. So, smooth symplectic variety is a smooth algebraic variety over complex numbers together with an algebraic symplectic form. And algebraic in particular implies holomorphism. We don't consider color forms. Okay? So a basic example, we'll take X to be C to N, to n-dimensional space, and put the standard symplectic form. Omega is sum from I from 1 to n, dxi with dx 2n plus 1 minus 1. That's smooth symplectic variety. Now, this is not a big deal. Definition of a singular symplectic variety requires some imagination, and this was done by Beauville. Into sum. This is also known as variety with symplectic singularities. So, according to Beauville, a singular symplectic variety.
So for you, varieties are affine, or
I can have affine or monophine, both of them. I'm most interested in affine varieties. So, singular symplectic variety X is, first of all, a normal algebraic variety and let me explain briefly what normal means. Informally, it means the singularities are not too bad. Formally, well, let's say for affine X, it means two things. It means that the algebra of polynomial functions on X coincides with the algebra of polynomial functions on the smooth ones. Smooth ones. That's one condition. The other condition is that the codimension of the complement is big or equal to 2. So this is what it means to be normal. Okay? Now, this is not all. So let me continue the definition. Such that the following two conditions hold. So first, I want the regular locus. So the regular locus is a smooth variety, the variety of all smooth points. So I want it to come with symplectic form. Let's say only. Okay? And then the second condition requires that there is a resolution of singularities well, let me write it rho from x tilde to x. Well, the phrase resolution of singularities just means that x tilde is smooth, and this map rho is first proper, second generically an isomorphism. Isomorphism over a smooth locus. I will give examples in a second. Okay? So such a thing exists always thanks to Kirillov. Now our requirement is that the pullback of omega, well, omega lives on x track, the pullback will live on the pre-image. We require that the pullback extends from the pre-image of x track to x tilde. Extends without poles. I can always extend with poles, but here it extends without poles, but maybe with zeros.
So the extension is required to be a homomorphic form, but it needn't be a symplectic form.
Absolutely.
Doesn't have to have zeros and still could be generated.
Well, I mean, yeah. So it looks like quite a definition. Why do we care? Well, first of all, it's a very nice problem. For example, once such a resolution exists, this is true for any resolution. And then variety with symplectic singularities is extremely nice from the point of view of algebraic geometry. For example, the Colloquium. So that's very nice. And as you may expect from things which are very nice, these are very rare. Let me give you an example to try to understand what's going on here. And the example is going to be a quadratic form. So I start with two-dimensional vector space C2, and I consider an action of the group of two elements, Z2, just basically by multiplying this plus and minus 1. And then I look at the quotient. My x will be C2 mod Z2. Okay? So how can I understand this quotient better? Well, let's look at the algebra of functions on x. The algebra of polynomials in x and y, which stays the same under changing the sign of both. Basically, they only include monomials of even power. And we can find generators for these polynomials. That's quite easy. So this is generated by three guys by an element which I will call A, this is x times y, an element which I call B, this is x squared, and an element which I call C, this is y squared. Okay? And among these three guys, I have exactly one relation. This relation tells me that A squared is equal B times C. And this is indeed a quadratic form.
A
Okay, sorry.
C.
A squared equal to this. Okay. That's indeed quadratic call, and if you open algebraic geometry textbook, this will have an exercise to check that this is normal. Normal variety. And now let's check conditions 1 and 2. Okay? So condition 1, well, what can I do? I can take the form dx wedge dy on C2, and this form is invariant. Is Z2 invariant? Therefore, it descends to the quotient where the quotient map is unraveled. So it descends to x without 0, which is precisely the set of regular points in x. So this does get a symplectic form. Now, I need something from the resolution of singularities, and in this case it's very easy to construct. I can basically take x tilde to be the blower of x at the point 0. And again, it's very easy to compute this thing. It's a cotangent bundle 2p1. And every cotangent bundle is a symplectic variety. So this is smooth and symplectic. And the real exercise is to check that the symplectic form here is obtained by lifting this. So, indeed, x is singular symplectic.
This is a case where the extension is actually symplectic.
Yes, in this case it's symplectic. In my further, I will give you a more general example where it doesn't. Alright, so this is a nice example, but of course you don't develop a general theory to establish just this example. There are several possible generalizations. One which is relevant for this talk actually goes back to Punisher. Generalization. Due to Punisher. So let's take, as usual, G, some semi-simple B algebra. And inside, I can take an adjoint order, which is the same as a coadjoint. It's a classical fact that on this orbit, you have a algebraic symplectic form. So this is smooth symplectic. This is known as Kirillov constant form. And then what I can do to get an affine and singular variety, I can take the closure. This is now singular and affine. But sometimes it fails to be model. Maybe not model. That's not a big deal. You can take so-called normalization. X normalization. And basically that's an affine variety whose algebra of functions is just the same as the algebra of functions of the orbit itself. And this guy is singular symplectic. Singular symplectic. So now we have much more examples, and they are considerably more interesting than what we get. But of course you can ask, why is this a generalization of the previous one? So let me explain. So special case of this example will be as follows. Our favorite V algebra for today is SL2. And inside, I can take the orbit of all non-zero nilpotent matrices. So X different from 0 such that the determinant of x is equal to 0. And if the coordinates here is a, b, minus c, minus a, then determinant is nothing else but bc minus a squared. And so the algebra of global functions on here will be just the algebra of functions on the quadratic form. So in this case, 0 for 0 is just functions on the quadratic form. So indeed I did get a generalization. Right. So now I told you what are singular symplectic varieties. I need to tell you about deformations. Okay? I'm going to deform those, and I want to explain what I mean.
You didn't really so is it easy to see that the symplectic forms are the same?
Oh, that's some exercise. I mean, hint use equivariance. Things are SO3 equivariant, and then you don't have much use. I mean, in coordinates, maybe this may be a bit subtle, but you know, with equivariance, it's quite.
I mean, you have to go through the entire yoga. Where does the symplectic form come from on a coadjoint orbit, right? So
It's the action by the dual on the Lie bracket of the vector field. But the vector fields have to be kind of annihilated by the action on the orbit. I just didn't see it.
Yeah, you use equivariance. This is good. All right. So let's talk about deformations. So let me explain what I'm going to deform. So I start with the Poisson algebra, A, and Poisson algebra means two structures. So this A is a vector space, dot is a commutative associative product, bracket is a Poisson bracket. So that's a Poisson algebra. And I want this Poisson algebra to be graded. Meaning that I decompose my vector space into the direct sum according to non-negative integers, so that the following holds. I take the product of AI and AJ, and it needs to lie in AI plus J.
Sorry, just to remember, so when you have a Poisson bracket, it doesn't have to be non-degenerate, is that right?
It doesn't have to be non-degenerate. Absolutely. It may be 0. So that's compatibility with the product. I also want compatibility with the bracket. Namely, I want that there exists a positive integer t such that the bracket of AI and AJ lies in A I plus J minus D. Okay? And you can ask me what is the example? Well, the same as before. So let's take A to be the algebra of functions of the quadratic form. This guy is graded by degree of a polynomial. And the Poisson bracket is given by a very simple formula. Sorry guys, the good chalk is gone.
So you could have done this without the Z2 equivariance, right? You could have just first.
Yeah, but without the two equivariance, this is boring. But this one is already interesting. And this is an example I'm going to deal with. You know, a big secret about this talk is that I'm only showing you instances of a single example. So, and what is a bracket? The bracket is, well, bracket G is df over dy, dg over dx, minus df over dy, dg over dx, dg over dy. And d is equal to 2. This decreases degree by 2. Now, I'm interested in deforming this, and I will consider two kinds of deformations. First, deformations called algebraic geometers are filtered Poisson deformations. What are those? Well, I leave the space the same, and I seek to modify the product and the bracket. I want a new commutative associative product, star, and I want a new bracket, which I will denote by bracket prime. So this is Poisson algebra. And the what's fielded deformation refers to the following. So for any homogeneous elements, f and g, I want to have the following conditions. First, I want f star g to be fg plus lower degree terms. Okay? And I want a similar condition for the bracket. The new bracket of f and g is the old bracket plus lower degree terms.
Lower degrees in terms of the grade.
Lower than the degree of this, which is degree of this plus degree of this minus this. Okay? Now there are deformations for representation theories, and those are filtered quantizations. So filtered quantizations are just associative algebras. Associative but generally not commutative. Such that one holds and also two holds where I replace this Poisson bracket with the Lie bracket of the associative column. F star g minus g star f. Okay? So that's the definition.
So you're saying the second is a special instance of the first?
No. In the first, my product is commutative. In the second, it's not.
But then you also get rid of the...
And now the bracket is replaced by something coming from the associative product, which is the commutative. Absolutely. Now, I want to identify some deformations. So we have equivalence on deformations from linear maps. Let me call it sigma from A to A, with the property that sigma of f is f plus lower degree terms. Once I have such a map, I can twist my structures with this map and get new but equivalent structures. I want to think of them as the same. Now, this definition is sort of elementary, but there is one problem with it, is that you cannot write these deformations in this way. You cannot really write the deformed products explicitly. So instead, we often use more active definition. And it says the filtered deformation curl A of straight A is a filtered algebra with an identification of the associated gradient with A itself. This is basically a fancy way to say the property 1. And now if you want to talk, say, about filtered Poisson deformations, you need to impose an additional structure on this curly area, Poisson bracket, and you need to impose some conditions, which is property 2. And similarly with coadjoint.
Sorry, I got stuck back here. So on equivalence on deformations, are you saying,
I want to consider these guys as the same.
you mean if you have such a map?
Then I say that such a map intertwining my operations, product with product, bracket with bracket, I say deformations are equivalent.
So you forget about the grading?
On this deformation, I don't have a gradient, I have a filtration. And this map preserves the filtration.
Oh.
My deformations are filtered. I cannot
they're not
deform
graded.
here in a graded way. Okay? So I will give you an example in a second, but let me state 2 main results about classification of deformations. In general, there is no hope to classify them. But the situation changes when this algebra A is an algebra of functions on an affine singular symplectic variety. So X will be affine singular symplectic. Like in my example here. So in the first result is due to Mimikava. In 09, and this result says that the deformation theory is as good as possible. Namely, there is a finite dimension of affine space which I will call A sub x, such that filtered Poisson deformations of A up to an equivalence are canonically parameterized by points of this affine space. Okay? And this is a natural bijection. This is very rare that in a deformation problem you get a simple answer like this. Now, a parallel quantum result is due to myself.
Affine space as additional structure, is that reflected in the structure of the deformation set?
So, when I say affine, I mean it's actually a vector space. There is a distinguished zero, which is an original algebra.
But for the rest, nothing else? Like addition,
Not really.
scale?
I mean, you can say a lot what the deformation parameters mean, and we can talk about this later. But for now, let me just state the quantum result.
So you're just looking at the underlying, just to Mark's question, so I understand. You don't care about the affine structure.
No.
Okay.
They just they're parameterized by some algebraic variety, which happens to be an affine space, as easy as possible. So, and then a result due to myself is that the same holds for filtered quantizations. So filtered quantizations of A are in a natural bijection with the same thing. And surprisingly, this result was unknown in most cases. Alright, now let me show you an example. And that's the same example as before, where A is the algebra of functions of the quadratic column. Or you can say that that's the algebra of functions on the important orbit O0, which is the quotient of C of SL2 by the conditions that determinant is equal to 0. that space of parameters is the same, and in this case it's just C. And when I take a point Z and C, the corresponding field of Poisson guy is what? It's well, it's C of SL2 modulo the relations of determinant is equal to Z. Or it's algebra functions on the orbit which I call OZ. Okay? And then field of quantization produced by this natural map will be U of G modulo U of G times the central element I meant for Fe plus H plus 1 squared plus Z. And you can show by hands in this case that these are all possible deformations of the specified kind. So in this case it's easy. When your algebra gets more and more complicated, you can imagine that the problem of doing this algebraically, it's impossible. Alright, so I told you about theorem involving primitive ideals. I told you about theorem classifying deformations. I need to tell you how the two fit together. So what's the connection? So this is the third part of the connection to primitive ideals. So what do I do? I need to take an adjoint orbit and I need to produce an ideal in the universal enveloping algebra. So let's do that. I take some O in G, that's an adjoint orbit. And then I can consider the algebra of functions. And this is a Poisson algebra. Now, a fact that there is a filtration on this algebra, making it into field of Poisson deformation of C of x, where x is a fine singular symplectic. Let's look at an example. Let's look at this example here. Well, my algebra is a quotient of polynomial algebra, and so it comes with a filtration, where coordinates here have degree 1. And then the associated gradient is, well, this. Algebra of functions on a singular symplectic variety. The general case is more complicated. You need to use some cohomology vanishing together with what is known as Lustig-Spottenstein induction to produce this filtration. That's quite clear. Alright. Now, what to do next? Well, I have these two theorems, which in particular tell me that there is a preferred way to take a field of Poisson deformation and produce a field of quantization. So from C of O, I produce a field of quantization. Let me call A. In example of SL2, this is the guy. Okay? And then, even in general, this A will come from with a homomorphism from SL2. From U of G. With a homomorphism from U of G. Which may or may not be subjective. But in this case, the homomorphism is obvious. Just a canonical subjection. And what I do, I take the curve of this homomorphism, and I get my favorite primitive ideal, and we just recover the map that I described in the very beginning. Well, I mean, in the end of part 1. So this, in fact, can be shown to be primitive. That's how the map is constructed. This is relatively technically easy. A hard part is to establish injectivity. So I told you that in almost all cases, the map is injective. And the way how you do it, you look at something called W algebras, and you look at restriction functions for Harish-Chandra bimodules, and using this you prove injectivity in almost all cases. In some cases, it doesn't work. All right. So in the remainder of the talk, which is like 3 minutes, I'm going to say something about how this parameterization come about. Okay? Where do I take these natural maps? Maybe I should be brief here. You know, at the end of the talk, you can scale. You may want to scale audience a little bit. So, maps in theorems 1 and 2 come from studying deformations of Q factorial generalization X hat. Well, let's say X. Now, what the hell does this mean? We know that X has a resolution of singularities which is not a symplectic variety in general. Now, Q factorial generalization, it's a maximal partial resolution. This guy is still singular, which is singular symplectic. Okay? It's still singular, and it's a maximal of this kind. And the existence is guaranteed by minimal model program. And let me not say more about it. Now, what you can do, you can speak about filtered deformations and about filtered Poisson deformations or filtered quantizations of the sheaf of regular functions on the smooth slopes. And those are naturally classified by the second cohomology of X hat track with coefficients in C. That's usually how the deformations are classified in nice cases. Now, AX that I've mentioned A sub X is the quotient of this set by certain finite reflection. And basically the way how you produce a relevant deformation from here, say a filtered quantization, you do the following. Take a point here, lift it to here, take the corresponding deformation of this fellow, it will be a sheaf, take the global sections and get an answer. And it in fact is a deformation. So that's how the parameterization works. And my time is up, so let me finish.
About this last thing, I got a little confused there. So you said that X hat is a singular symplectic.
Yeah, but it has better singularities.
Oh, the Q factorial.
Yeah, terminal symplectic.
The terminal singularities.
So the point is that when I do this, I basically resolve all Kleinian singularities appear. Kleinian, all singularities in codimension 2. Okay. So, you know, if you have a symplectic singularity in dimension 2, it's a quotient of C2 by a finite subgroup of C2. And those have very nice resolutions which have been studied for, I don't know, for ages. And so basically what you can show is that you can find a resolution which kind of resolves all these codimension 2 singularities. And then you only have singularities in codimension 4, and the life is not so bad.